time going over the old stuff, unless you guys have particular questions. Electronegativity is going to keep coming back. Okay, so I'm going to keep showing this slide, trying to convince you that you need to know it and be familiar with how to manipulate it, because it's going to keep showing up. After that, Lewis structures. You need to be able to draw your Lewis structures. Yes, the final is all multiple choice, so you don't have to draw a structure per se, but if you take a look at the last few questions, I think they're the last few questions on this exam, there are questions about how many bonds does this structure have. Okay. Well, to know how many bonds it has, you have to be able to draw the Lewis structure. So they can still get at making you draw out an appropriate structure without grading for that. Okay. Shape summary. You need to be familiar with your shapes. If you're moving into 151, you're going to be adding on top of this. Okay. You get even more shapes over the top. Wow, that was it. Okay, any questions? How are you guys feeling with Lewis structures and shapes and stuff? Good? Yeah-ish. Okay, that's reasonable. I can accept that. What? Stop going to the hexagon.
I had to figure out how it works. So I got little models in the lab and made it.
You made it? Okay. Yeah, that'll work. So, Chapter 7 is about chemical reactions. Okay. Kind of weird because we end up covering a little bit of nomenclature and a little bit of everything else, charges and all sorts of other fun stuff when we look at our chemical reactions. This is really where we go back and talk about our chemical and physical changes, and now really you're starting to build some knowledge on what is going to make a chemical versus a physical change. Okay? So, because now we've got reactions to look at, so we can look at what happens to our reactants as they go to products. This helps us with our chemical and physical changes. So in our physical change, the composition stays the same. Okay? We don't make or break any bonds. When we look at a chemical change, we're going to make or break bonds. Okay? So we get a new substance coming out of that. So if we looked at a reaction, we could then start to predict, oh, that is a chemical change because I've changed where the atoms are connected or what they're connected to. So evidence. Okay, again, I think we've already seen, we did talk about this slide earlier, beginning of the semester. I at least tried to copy it forward. We've got what I would argue are really only 3 examples of chemical reactions. Okay? And yes, there are exceptions to these with your physical reactions, but these are kind of our primary focuses. Your textbook classifies the first 2 as 2 separate steps, which I think is kind of silly, but it's really just one thing. We're looking at a change in phase. Okay? So if you change the phase from, say, a solid to a liquid, okay, or a liquid to a gas, or a liquid to a solid, it's really one of the signifiers for a chemical change, not a physical one. There is one big caveat to that. Okay? That caveat is that there is no heat included. Okay? That means if I take a pot of water and I put it on the stove and I heat it up, that is a liquid going to a gas. That is a phase change. Okay? But I supplied the heat to cause that phase change. If I just mix 2 liquids and now I see gas, okay? Even if those 2 liquids now release heat and it gets hot, I did not supply the heat. If I do not supply the heat, that is a chemical reaction, not a physical.
What about when you heat iodine and it makes that purple gas?
Heating iodine is also an example of a physical change. What's happening when you heat iodine? We're providing enough energy to the solid that it turns immediately into a gas. The gas happens to be a purple vapor due to concentration. It appears purple. The crystals are also purple. They don't look purple because the concentration is now so high in that individual point that we end up seeing a silver color instead. So in that lab where you heated up the iodine, in theory what you should have done is cooled it down once you saw that purple vapor, and hopefully what you saw on the sides of that test tube was this weird dust-looking stuff that wasn't there before. Guess what that dust-looking stuff was? Iodine solid. Okay. So what we ended up doing was a phase change in that circumstance. Okay. So we got a nice little example. I keep forgetting these images. We got gas forming. So when we mix baking soda with vinegar, we see a gas form. We just mixed 2 materials. We didn't supply heat. So if we see gas, guess what? Chemical change. I saw a thought in your head. What's the thought in your head?
That was magnesium acid.
I have no idea what that was, actually. Looks like it. Looks like it was magnesium and acid. The other one is seeing a solid form. Most commonly, you'll see these show up, at least in textbooks, with these big brightly colored solids because those look prettier. Very typically, when you're looking at a solid form, the color of your solid happens to be white, which is very boring. Okay? So very rarely does that show up in a textbook, but you see it all the time in the lab. Okay? How do you know you have a white solid forming? It may sound like a simple question. It's a little bit harder than you may think.
Turns white, floats to the bottom.
Okay, so what most people look for is that solid settling to the bottom or potentially floating on top. But what if your solution turns cloudy? Why is it turning cloudy? Said another way, why is light not passing directly through the sample?
Yeah, a lot of small particles.
There's a lot of small particles that the light is impacting and is not directly passing through the sample, which means it looks opaque. What are those small particles? That solid. It just didn't solidify enough to see a solid precipitate settle to the bottom or potentially float on top. Okay? Other big ones, permanent color change. If you mix two clear solutions and the result is now a blue solution, that's a permanent color change. But if I mix a red solution with a clear solution and I get a pink solution, that's just a dilution. Okay? That's not officially a chemical change. Okay? So adding food coloring to white frosting, physical change, not a chemical, even though there is a color change of the frosting. Okay? You look way too excited today. An energy change is observed. Okay? That's probably the last one. It shows up in probably all of these types of reactions. You'll see an energy change. How do we monitor our energy? Stick the energy probe in, it says, oh, it's 50 kilojoules. How do we measure energy? Heat, which is ultimately temperature. So we use temperature as a way to kind of define if there's an energy change in the course of the reaction. Again, if we're seeing this energy change or our temperature change, it's not one that we induced. We don't look at a solution and say, oh, it's getting colder, it must be a chemical change. Never mind the fact that I'm sitting in a freezer. Okay? That it's a physical change. Okay? Or, oh my gosh, the solution's getting hotter. That must be a chemical change. Never mind the fact that I got a Bunsen burner on the bottom of it. Okay? So if we supply that heat, that's not a chemical change. Okay? So what we're looking at is taking two solutions, or a solid and a gas, any one of those combinations, we put them together and boom, something happens. In that boom, something happens. If we see a release of heat, the temperature gets warmer, it's an exothermic reaction. It's just a fancy way of saying exo for outer, thermic for heat. So what's happening in an exothermic reaction? Heat goes outside. Okay? Sounds like a children's book, right? Heat goes outside. Man, I'm trying. Okay. That will typically correspond to a negative symbol if you're going to look at the mathematics on. If we look at heat being absorbed by the reaction, we get an endothermic reaction. Thermic, again, for heat, endo for inside. It is our heat going inside our reaction. Simple as that.
Heat didn't like it outside, so it's inside.
Sure. It's the parent book to exotherm.
The other reactions made from them.
Yeah. So we can look at another release of gas, and ultimately you're seeing flames here. Why are we seeing flames in this case? This is actually an interesting one. What did we add to it? Water and
Sodium.
one of our alkali metals, or alkaline earth, one of those, react very violently with water. In that chemical reaction, they release hydrogen gas, but they're also releasing a lot of energy. They release enough energy to ignite the hydrogen gas, and we now get a second reaction of hydrogen gas burning with oxygen. So by just adding liquid or water to sodium, we can get 2 chemical reactions happening as long as we're in standard atmosphere. Kind of neat. It'll still release enough heat. It may not release enough heat to ignite the hydrogen. So, what information does this equation give us? You look at that. Can you give me any information about it? What was it?
Something gets turned into an acid?
Okay, we'll go with number 1. Something gets turned into an acid. Why did you say an acid?
AQ?
You see the AQ. Think back to our definition of acids. Is it just AQ? Is a hint? No. It's not just AQ. What has to be present for that to be an acid? We have to have a hydrogen there. Is there a hydrogen written there? No, so we don't know that that's an acid necessarily. So what does AQ mean? Aqueous, which means not quite a liquid. Dissolved in water. Okay. So it's an actual phase. We're specifying the phase on molecule D. That molecule is now dissolved in water. That's what that means. What was the next part? I heard S is
Molecule C is a solid.
molecule C is a solid. Molecule B? Molecule A? Gas. So what information is provided within this?
States.
Physical states. So our equations typically give you physical state information. What else? What's that?
They really provide the state of the
Not in the homework.
substance? I mean,
In chemical reactions, in Gen Chem, you are provided the physical state. Yeah. That's why I don't like Gen Chem, because I don't like writing those stupid parentheses. And yeah, if you go through and push this into 151, and we'll look at some other reactions, you're required to specify the state for every molecule. Yeah, it gets tedious really fast. What else is given? Don, what did you say earlier? You said something about something turned into something? Did you say that? Did you say that? You guess so? Good. Let's say you said that. Something's turned into something. How do you know turned into? Where's that turned into coming from? We have a reaction occurring. That arrow tells us that we have a reaction. We have a turned into, if you will. Okay. Which means we have even more information. What is different about A and B versus C and D? A and B are reactants, sometimes also referred to as reagents, depending on who you talk to and what you're doing. And C and D are typically referred to as products. Okay. What other information is given to us? Is E involved in the reaction? No. We're actually being told the molecules that are being involved in this reaction. Not only are we being told the molecules that are involved in the reaction, but we have a little bit more information about them. How many molecules of A and how many molecules of B are involved in this reaction? How do you know that? There's no other coefficient supplied in front. So we can look at the number supplied in front, and we now know how many. That should be a W. How many molecules involved? Yeah. We could look at neutrality, okay, which is slightly different from what the equation's giving us, but how are you implying neutrality?
There's no charge given.
If we look at the upper right-hand corner for every single one of these, there is no charge written, which means each of those is neutral, zero charge. I would argue that's not something given to us by the equation, but something given to us by the formula. Okay? The formula of D says that it's neutral here. Okay? In a real problem, instead of having just the first 4 letters of the alphabet, we'd probably have some other atoms in there, molecules. And we could then imply how many atoms of each are supplied. That's what our formula gives us. Our equation is giving us a little bit more. There are a variety of other things that can pop up in a reaction. Your textbook lists off a whole bunch of them. Okay? One of the ones we missed, plus sign. What did the plus sign mean? I would argue it's not even reacts with, because the plus sign on C and D is not a reactant. Those are products. The plus just means and. There's something else there. There's another thing present. Right? The next one shows a little delta symbol. Everybody know what delta is? It's a little triangle over our reaction arrow. What does that triangle mean? Ultimately change. When placed in a reaction, what does that mean? It's a change in temperature, which we have implied as increasing the temperature. So if you see that delta symbol around a reaction, what does that mean? We've added heat. Not just that it gets hotter, because that's something that the reaction did. If we see that delta symbol, we added heat to cause this to occur. Okay. Next one, you see a little Fe over the arrow. What is Fe? Iron. What is iron representing in this case? Same thing as heat. We are adding iron just like we added heat to our reaction. Why is the iron not written in the reaction and instead written above the arrow? Sort of. Iron is known as a catalyst, which then brings the next question. What is a catalyst? It's something that speeds the reaction by ultimately changing how the reaction works, but at the same time is not consumed in the process of the reaction. So if I included iron as a reactant, what do I also have to include iron? Or where do I have to include iron? As a product. So I end up writing it twice, or write it once over the arrow, and I'm done. Yes?
Iron just a kind of a universal reactant, or are we going to see others besides iron written?
You probably will not see a catalyst at all, at least in this class. If you move into other classes, you'll sometimes see it specified, and they usually make it less ambiguous by doing this. Anybody see what that says? Cat for catalyst.
I mean, would there ever be like an I over the catalyst, or
Like
C,
iodine, any one of the other elements, yes. Yeah, you can see actually complex molecules show up as catalysts as well. It doesn't have to be just a simple element. NR for no reaction. So if no reaction occurred, we wouldn't actually write out C and D. Because C and D didn't actually form, we would have to write NR. Okay. Then you've got all your phases, right, what those phases entail within them. Okay. Does that mean every time you see a chemical equation, this is the format you're going to be given? No. In Gen Chem, it's going to hold pretty true. Okay, you don't have to stress too much about that. In organic, we take all the rules you learned in Gen Chem and use the ones that we like, and we ignore the ones that we don't. Yes?
Well, sorry, what would be the basis of a non-reaction? I mean, like, in lab, you can certainly see if this and this goes together and nothing happens. I mean, on paper,
That's it.
What would be like?
So what that's actually getting to on deciding no reaction is predicting the reaction. Are you expected to be able to predict reactions?
No.
Yes. Okay. Before you can predict the reactions, you have to know what type of reaction it is. Once you know the type of reaction, you then have to decide, is that something I'm supposed to know or not? And we will talk about that in this chapter. Other questions on that? Okay, this is something that I think should have shown up in the nomenclature chapter, and I always forget to talk about it. So if we look at this nice chemical reaction, what we could go through and do is look at what things changed in the course of the reaction. So take a minute here and just look at that reaction. What things changed? All we're trying to do is say, where did atoms shift around? So first question, did anything change? Yeah, okay. What changed? Okay. This hydrogen swapped with that sodium. Okay. Which then meant that the other two also had to swap. Whoops, I didn't circle that right. No, I did. Those two things swap out. So we end up with sodium now in front of what species? Acetate. How do you know it's acetate?
There's an oxygen and a hydrogen in it.
I beg to differ.
AQ.
Is that acetate?
Put the AQ in there too.
I'll put an AQ in there too. That's still not going to change it.
Wait, what? I'm so screwed for nomenclature today.
It's okay.
It's just a mid.
C2H3O2 is acetate. You know it's acetate because from the nomenclature section, I told you to have that memorized. Okay? That's how you know that's acetate. The other hydrogen exchanged and is now partnered up with our first hydrogen. Why did we not just write H? Why do I have to write H2? There's two of them. Okay? It's an interesting idea. Do I have two hydrogens now? What does the 2 in front of the H mean? There's two hydrogens. Do I have two hydrogens if I write 2H? Yes. There's two separate hydrogens. So why do I have to write it as H2 and not 2H? Because those hydrogens are bound to each other. There are certain elements that will bond to each other or bond to themselves in very specific ratios. Okay? The most common one that you're going to be concerned about is the diatomic elements. Hydrogen happens to be one of them. Di for 2, atomic for atom or atomic. So hydrogen being a diatomic element, in its natural state, there will be two hydrogens and they are bound to each other. We signify that bond by putting the 2 as a subscript because that 2 is now implying a formula for hydrogen. Okay? The 2 in front is now not a formula, but saying how many of whatever follows after it. So two different meanings, no pun intended. And that one was a long shot. That was a real long shot. So there are 7 diatomic molecules. You are responsible for knowing that these are diatomic. So if they show up, you need to know that you have to show them as H2 or Br2 or Cl2. So there are a variety of ways to go through and memorize this. The one that I've memorized was the nice little phrase, have no fear of ice cold beer. Okay? Gets pretty darn close to looking at the first letter of each element. Symbol for hydrogen is H. What does have begin with? H. Look at that. Okay, so it matches up pretty well. The other one that I've heard some people mention, which only sort of works and I don't really like it, but they say, oh, it's a 7 plus 1. Right, which is why I'm like, I'd rather just remember have no fear of ice cold beer. Okay, so you've got the hydrogen and then you've got your 7 there as well. Okay, so you need to know that those elements are diatomic. When we write them in formulas, you have to show them as being diatomic in their elemental state. Okay, why did I not show the hydrogen as diatomic in sodium hydride? Instead of hydrogen being bonded to hydrogen, it's sodium bonded to hydrogen. Okay? Different system because it's not hydrogen by itself. Okay? It is hydrogen in a bond with something else. Same deal for, oh, awesome, there's a nice delay on this. Yeah, we just lost the internet connection. Between the acetate. Yes?
So, just by looking at this formula with the parentheses, we would be able to say that we put a solid of the sodium and the hydrogen into the liquid. What happened was that hydrogen gas was released.
So let's convert that statement or that equation while I'm hopefully waiting for the internet connection to kick back on into a sentence. So we have sodium hydride. How do we know to call it sodium hydride?
That's what it is.
Because you're awesome at your nomenclature rules that you've got nailed down from chapter 6. Okay?
Yes.
Taking a step further, it's not just sodium hydride, it's solid sodium hydride reacting with the next one? I would start underlining things, but it's not going to work. Maybe it's back. Yeah. Oh, cool. We're back. Here. Someone said it. It's an acid. So we now have to know how to name our acids. Which type of acid is this? Binary or ternary? Ternary because more than just two elements. Right? So in our ternary naming, we have to know the name of our complex ion, which we just said was acetate. When we're looking at naming an acid, we change the E to ic acid. Sorry, that 8. I can spell. Hey, if you guys are tired, I'm allowed to be tired too. We've got acetic acid. Okay. So we are taking solid sodium hydride and we are reacting that with acetic acid. What phase is the acetic acid? It's dissolved in water. So I'm taking solid sodium hydride and reacting it with aqueous acetic acid to produce sodium acetate, aqueous, and hydrogen gas.
Sodium hydride wouldn't react with the water too?
No. Okay. So you are responsible for going both directions. One way is just strict nomenclature. One way is just looking at the equation and processing all the pieces. Other questions? That was a good one. We'll keep coming back to that. Okay. Let's bring in some numbers. Balancing chemical equations. When we write out a chemical equation, the number of atoms in each element on each side of the reaction must be the same. Why?
Resonance.
Not a bad guess, but no, not resonance.
Can't destroy matter.
We cannot create or destroy matter. Okay, which means if I start with one sodium, I had better end with one sodium. Okay? So we need to come up with some way that we can balance this out. Some people are really good at doing this in your head, particularly with simple problems. Some people are not. I would highly recommend that you pick up a pattern that allows you to do it consistently every single time. So let's go through and take a look at two methods for balancing this. Number one, we need to balance each element. So what element do you want to balance first?
Carbon.
Carbon. Way to pick a hard one, but okay. It's not that hard, I guess. How many carbons are on the reactant side?
2.
How do you know that?
Subscript 2.
The subscript 2 applies only to what's directly in front of that, which happens to be carbon. There's 2 carbons on the reactant side. How many on the product side? 2, for the exact same reason. Are carbons balanced?
Yep.
Yes. What do you want balanced now?
Hydrogen.
How many hydrogens on the reactant side?
5.
What?
5. 5. H3, H, and then H.
Where are you seeing? Oh, yeah, never mind. There's a 3 there. I didn't see it. Holy crap. Okay, let's try that again. Hydrogen, hydrogen, and then this 3 hydrogens, which means we have...
5.
Frick. It's horrible. Take a vote. You guys can teach yourselves. How many hydrogens on the reactants or product side? 5. Hydrogens balanced?
Yes.
Yeah, what do we do now?
Sodium.
Sodium. How many sodiums?
1.
How many sodiums on the product side?
1.
Is it balanced?
Yeah.
What do we have left? How many oxygens do we have? 2 and 2. What does that mean? It's all balanced. Oh, all that work and it was already balanced. How many of you saw it was already balanced before doing that? Good job. Okay. Another way we could have balanced this. I know this is a simple one. You're like, we don't need to balance it. Do we need to balance this one again? Should we try a different one? Okay, let's try a different one. Okay. So what we want to be able to go through and do is pick up that method and balance our equations. So we set up some kind of guidelines as we went through and did that. Okay. The very first step for balancing equations is predicting products if necessary. Have you learned how to predict products yet? Don't worry about step 1 yet. Okay? We might be able to predict products by the end of today. Now you need to do is balance your formulas. Make sure your formulas that you're working with are correct. Okay? The only time that you should be balancing formulas is right after you've predicted products. Okay? Well, if you haven't had to predict products, do you need to balance formulas? No, we're giving you formulas at this point. So you don't need to stress about that part either. Okay? 3, pick any atom you want and balance the equation, okay, with that atom, just like we went through and did starting with carbon in this case. Okay? Typically, it is best to balance atoms other than hydrogen and oxygen. Okay? For most of the problems that you will encounter this semester, that's not a big deal. Okay? But it may pop up where you want to balance them last instead of first. To go through and balance, you will put whole numbers in front of formulas to increase the amount of atoms if they aren't already balanced. Okay? You then go through and repeat that work for every element on each side of your equation to make sure they balance. This gets to the fun part, because most people stop at step 5. Okay? Extremely frustrating as an instructor. Okay? Because what is step 6? Check your work. Why? There is no reason you should get a balancing question wrong. Okay. Why? The number of atoms had better equal the number of atoms. What we're doing is 2 equals 2. Okay. It is admittedly a little bit more complex than that because of all the little pieces that go into it, but that is what you are checking. So as long as you go back and check your work, it will work. Okay. And you will get the correct answer. This checking your work process should be repeated anytime you change a number in front of an equation or in front of a formula. It should be repeated even after you haven't changed any numbers. And it should be repeated again. And guess what? Do it again. Okay? And again. Okay? You should be at that point, really, this is what I'm pushing for. That you've checked it so many times that you're like, Mike is an absolute jerk for making me check this so many freaking times. That's the emotion I want out of it. Okay? Because if you're pissed at me, you remember. Okay? And you will not get it wrong on the test. Okay? The last absolute step that you have to watch out for, because sometimes you may have made a mistake somewhere along the lines, you need to verify that you've used the smallest whole numbers possible through your equation, through that balancing process. Okay. That is critical for our overall balanced equation. By definition, we have to use the smallest whole numbers. Okay? So, now that you're all experts, we'll give you some time. So, next one. H2, Br2, HBr. What'd you guys get? 2 HBr. This is a good time to go ahead and bring in another question on this. I heard a want-want. What's the want-want? Okay, which is going to get to the next question, so let's hold that thought. How do I ask this question on a test? Say balance the equation. Okay, but your test is multiple choice.
Which of the following is the correct balanced equation?
So I could go through and do which of the following is the correct balanced equation, but what does that mean I have to do? I have to write the correct balanced equation once and the incorrect balanced equation 4 times. You have way too much faith in me if you think I have that much time.
How many of this is there given this?
So I could say, in the balanced equation, how many HBRs are necessary? What would you say? 2. Another way that this typically comes out, and most people get confused by it, and I don't blame you, is what is the sum of the coefficients of the balanced equation? Yeah, should I actually write that down? I know. Sum of, it's very common, coefficients of balanced equation.
Or you could do like, what's the correct order of numbers?
We could try something like that too. I like to see one easier. So what is the sum of the coefficients of the balanced equation? You add them all up. one of the most commonly miscorrected answers, or mischosen answers in this case, ends up being 2. Is 2 the sum of the coefficients? No, because what's in front of the H2 and the Br2? 1 in front of both. So the sum of the coefficients is 1 plus 1 plus 2, 4 is your correct answer. So when it comes to balancing questions or balancing equations, you can see it in a show your work kind of place. You can see it in the multiple choice very quickly and easily, and be careful because all we may be asking for is to balance one of them. I only care about the coefficient in front of H2. Okay, well, if I only care about it, it's a 1. Okay? If I only care about the coefficient in front of HBr, it's a 2. So you have to be careful on what the question is asking. Read your question carefully and make sure you answer it appropriately. Okay? Is that something about a fall?
Oh, yeah.
Oh, I saw you looking up, making me nervous. Oh, it does that. It scared me. Just keep letting it go. Last one ends up just being 1s all the way through. That's kind of a straightforward balancing one. So I'm going to just kind of skip that one and move to this second to last one. So there are 2 ways that we can go through and balance. So far what I told you was only balance based on the elements. So we'd look at aluminum, we'd look at sulfur, we'd look at oxygen, we'd look at barium, and we'd look at nitrogen. Okay? That is a possible way to go through and balance this. Some of you are already violently shaking your heads. It's not wrong. Give me a break. Is there an easier way to do it? Okay. What we can do is go through and balance based on the things that did not change. I don't have to balance sulfur and oxygen. Whoa, I forgot. There's stuff hidden under there. I can balance sulfates. Why can I balance the sulfate? It didn't change in the course of the reaction. I start with sulfate, I end with sulfate. I may change what it's bound to, but it's still sulfate. So as long as that doesn't change, I can balance that as a unit, which means I can then balance the barium, and I can balance the nitrate. Okay, officially with a -1, 2. So, where do we want to start balancing? Okay. Some people, I noticed, randomly jump to balancing the sulfates and the nitrates first. I probably would not have done that, mainly because they're complex ions and those confuse me. So what I want to do is balance things that aren't confusing. Aluminum looks a little bit more straightforward. How many aluminums on the reactant side? Sorry, yes. How many aluminums on the product side? 1. So what do we need to do?
2.
Put a 2. Okay.
No.
What's wrong with that?
That means it's bonded to itself.
I'm changing the formula. I cannot change the formula when we start balancing. The 2 needs to go out front. Okay? So I had a 1 that's now become a 2. My aluminum's balanced. Now what do I choose to balance? Why barium? It's nicer than the other ones. I agree. Let's do that. How many bariums do we have? 1 and 1. Well, that didn't change anything. Oh well. So that looks balanced. Now what do I want to balance?
Nitrate.
Okay. Nitrate or sulfate. It ultimately doesn't matter. We just get to go through and decide. So let's take a look at the nitrate first, because I think that's what I heard first. How many nitrates on the reactant side? How do you know there's 2? The subscript 2, subscripts always apply to what's directly in front. What's directly in front of that 2? I want to be a little bit more specific. It's not nitrate. The parentheses. Okay. What is within the parentheses? Nitrate. So now how many nitrates are there? 2. How many nitrates on the product side? Okay. I heard a 3. I agree. There is a 3 there applying forwards. But there is also a 2 applying backwards. The number in front applies to everything after it up to the plus sign, which means how many nitrates do we have on the reactant side? 6. Are we balanced? No. So what do we have to do? I don't know what add 3 means. Put a 3 in front of the barium. Why am I confused by the adding 3? If you add 3 and 2, that's not going to be right. What are we doing? We're multiplying, and we get 6. Okay? Now we can check our sulfates. How many sulfates? On the reactant side, 3, and on the product side, 1. Is that balanced? So what do I need to do? Multiply by 3 to make that a 3. Okay. Now my sulfates are set. Now what do I do? Check the whole thing again so we can start back with the aluminums. How many aluminums? 2 and 2. How many sulfates? 3 and 3. How many bariums? 3 and 3. Oh, so the numbers changed, but they changed in such a way that they were already balanced. Well, that's nice. Okay. Nitrates? Now what? Do it again. Then what? Do it again. Are you irritated yet? Do it again. How about now? Okay. Keep doing it. Okay. That is what balancing will do for you. You have the answer there. You just have to make sure you check it enough times to verify that it's there. Okay. All you're doing is just do the atoms count up right. Okay? Questions on balancing? Yes?
Are you able to break it down like the SO4 into sodium by itself and then oxygen by itself, but you know to do the subscript 3 to both? Because that's how I did it. I got the same thing.
Yes, I see what you're saying. Almost. S is what?
Sulfate?
Sulfur?
Sulfur?
Okay, but yes, now I agree with you. So if you're going to break it down to sulfur and oxygen, how many sulfurs are on the reactant side currently? There is 1 sulfur in sulfate, but there's 3 sulfates. There are 3 sulfurs on the reactant side. So you can break it down and look at those individual pieces, and it will work. You're balancing 5 things as opposed to 4 things. Okay? It depends on your preference on how you decide to go through and do that. I personally will keep the complex ions. Okay? Other questions? I changed my mind. Classifying chemical reactions. Mainly because I don't have any papers. I wasn't kidding about that. I used them all. Classifying your chemical reactions. So the rest of this chapter is now looking at, was that 5? I've been miscounting. 2, 3, 4, 5 different reaction types. You're responsible for being able to classify any reaction that fits in these categories. So what we've got here is a rough summary of what's happening in each of these. Sometimes the names actually make sense to what's happening within it. So if we look at a combination reaction, if we look at a combination pizza, what do?
Throw it all on there.
You put all of the ingredients onto one pizza. So if we look at a combination reaction, what are we doing? We're taking all of our reactants and we turn them into one thing. There's a combination reaction. Right. Decomposition reaction. What's happening in the decomposition? You're breaking it apart into smaller pieces. So you start with one thing and you turn it into multiple pieces. Okay. Oh, yes, salt dissolving in water, yes. Single replacement reactions. We take a look at the single replacement reaction. What's happening in the course of this reaction? A is by itself, and it is now in the product side. B was replaced by A. We did a replacement. How many atoms did we replace? 1, hence single replacement. If we move to the double replacement, what's happening? We switch 2 things. We now have a double replacement. Take a look at the last one, a neutralization reaction. Can you classify the neutralization reaction as something else? Acid and base is technically true, but let's go based off the 5 combination types we've got. Is it a combination reaction? We take 2 things. Do we make 1 thing? No, there's 2 things there. That's what the plus means, right? Did we take 1 thing and turn it into 2 things? No, we took two things and turned it into two things. Do we take three things and turn it into two things? That's not three. Do we take two things, turn it into two things? Well, that's two and two, but is that what happened? Is that the only thing that has changed? No, something else happened. What type of reaction is a neutralization reaction? It's also a double replacement. Why do we refer to it as a neutralization reaction? If we include our phases, you very commonly see that first species starting with an AQ. Why is that important? What do we have, Pierre? We have an acid. Okay. If we have an acid, what happens in the course of this reaction? If we look to our products, we don't have an acid anymore. We neutralized the acid. Hence the neutralization reaction. It is a very special double replacement because acid-base chemistry carries a special place in our hearts because we get burned by it. Right? So it wasn't intended to be funny, but I'll take what I can get. Okay? So those are all of our chemical reactions. What the rest of this kind of sequence is now going to look at is individual examples for each of these. So we take a look at a combination reaction. Okay? You're not expected to predict the products of these because the ratios of these can be a bit dicey. Right? So there are certain circumstances where you're kind of expected, and that's these very particular things that they're mentioning in between. Okay? So we've got these three primary reactions. The reaction of a metal with oxygen, the reaction of a nonmetal with oxygen, and the reaction of a metal and a nonmetal. Okay? So if we go through and take a look at magnesium metal reacting with oxygen gas. Okay? So which does that classify as? 1, 2, or 3? Why do you say 1? Okay, it's a metal with oxygen, which is a nonmetal. And thank you for pointing out the color coding. They're both red. I spend some time. Let's turn it into a formula. What's our formula for magnesium? What was that? Mg. Plus YO2. It's a diatomic element. Okay, that's our of. Okay, and have no fear of ice cold beer. Okay, those will then react to produce a combination of the two, Mg and O. Okay, this is where this reaction can become a little bit dicey. I do kind of expect you to be able to work your way through this. Okay, so let's make sure our formula is correct. Okay, is this formula correct?
No.
Why do you say no? Why is it not balanced? Why is it missing an oxygen? Did I ask anything about the reactants? I only asked, is this formula correct? That formula has nothing to do with what made it. It only has to do with making sure that it balances out and produces the neutral product. If I combine magnesium with oxygen, do I generate a neutral product? Some people are shaking their head yes. Some people are just saying sure. How do we know this is our neutral product?
That's what it is.
Magnesium is a +2. How do you know that?
Memory.
You can either have it memorized, or if we remembered back to our patterns, our second column on our periodic table all have a +2 charge. What's the charge on oxygen? -2, which again goes back to that memorization, or -2. I'm fine with that too. When we put those two together, does that neutralize the charge? Yes. Is this the correct formula? Yes. Now that I have the correct formula, now I can balance the equation. Is the equation balanced?
No.
Not balanced. I need to balance it. I do that by doing what? 2Mg and 2MgO. Now I have my balanced equation. Okay. This is the part of remembering. You have to balance your formula before you go through and balance the equation. If we dropped a 2 next to that oxygen, we might be able to balance the equation. In fact, in this case, we would have been able to balance the equation, but we would have balanced it wrong. We would have gotten the wrong answer. Very often, what will end up happening is you will not be able to balance the equation. Okay? If you get to the point where you cannot balance the equation, what should you do?
Start over because you bounced too far.
Start over where?
Beginning.
What's the beginning?
Before the roading thing.
The formulas. Check your formulas. More often than not, that's where your mistake was made. You tried to balance an equation with improper formulas. So check those. We'll pick up there on whatever it is next Wednesday.